Good morning, everybody. The learning objective for this lesson is to investigate the internal resistance of a source. The success criteria are define the internal resistance of a power supply or an EMF source in a circuit, deduce an expression for the terminal voltage or load voltage, determine the value of internal resistance from a VI, terminal voltage versus current graph. Let's get it started. So, first of all, what is internal resistance? Now, we have already come across the term resistance uh, by referring to different circuit components in a circuit, like resistors, for example, or thermistors, or let's say a diode, or any other circuit component. Now, the resistance that we are talking about here has a slightly different meaning. uh, we all if we have ever gone through any question, past paper question for electricity or electric circuits, you may have noticed that some questions have this line mentioned, this is statement: the internal resistance of the battery or the power supply or the source is negligible. Now, what does it mean? So what happens is, when a power supply or a source of EMF helps current flow through a circuit, the charges, as they flow through the source itself, there is some energy that the charges lose within the power supply itself. So, if I want to put it into perspective, think of a battery. Let's say, think of a 9-volt battery, 9 volt or 1.5 volt AA or AAA cell. Just think about that. If you take a multimeter and try to find out the EMF across the two terminals, the PD across the two terminals without connecting the power supply or the battery to any external circuit, you will be able to measure the volts, the PD available across its terminals. Okay. Now, the same power supply or the same battery, when you connect with a circuit, a working circuit, just a simple circuit, perhaps just a lamp connected to a battery, a small bulb connected to a battery, if you repeat the process again and you try to measure the PD or the voltage across the battery itself, now you will see a smaller number. Now, why does this happen? So, internal resistance of a battery is actually the resistance provided by the battery itself as the charges flow through it. We have already learned about EMF. What is EMF? It's the electrical energy. It's the energy provided to the charges per unit charge, and it is some other form of energy converted into electrical energy. Now, when the battery does so, the charges have to flow through the battery, and in that process the charges need to overcome some resistance within the battery itself. This is how all real situations work. We can never have a situation with zero resistance. We all know about that. Ideally, we can consider whatever is the EMF, the rated EMF of the battery, the same is the voltage or the EMF supplied by the battery when it is connected to a circuit. But practically, a 9 volt battery may have a rated EMF of 9 volt, but once it is connected in a circuit with some load means any external component, a resistor, a lamp, or anything, once it is connected in the circuit, if you try to measure the voltage across the two terminals of the battery, you will always get a value smaller than the rated EMF, which is in our example 9 volts. So, how do we define internal resistance? Internal resistance is basically the resistance provided to the flow of charges within the source of EMF or the power supply itself. It is the work done in driving the charges within the supply. Okay, so now moving ahead. To visualize this concept, there's a circuit diagram in front of us. Now, how do we try to represent internal resistance of a source in our circuits? You can see in the circuit diagram shown, there is a source, a power supply or a battery, and a source of EMF with a rated EMF as E. There is an external resistor R, or just a resistor R in the circuit, and you can see there is a flow of current. There is a current I flowing through the circuit. Now you can see there is a dotted box made within which they have shown a small resistor R next to the power supply. Now, what does this R represent? This R represents the internal resistance of the power supply itself. So, in our circuits, usually the circuits that we have been making so far in IGCSE or even now in this at this level, we usually just show a power supply or a source of EMF. But even in that source of EMF, there is always some internal resistance. So, just to represent that internal resistance in our circuits, we make a separate small resistor R next to the power supply. But of course, in reality, we do not, in actual circuits, practical circuits, we don't see this as an external resistor. This resistance itself is part of the power supply or the source itself. Now, if you consider this circuit and apply KVL, Kirchhoff's voltage law, or the voltage rule on this particular circuit, which is, if you remember, if you recall, total EMFs is equal to total voltages. So the EMF source here, or the EMF here, is E, the total EMF provided, because there is only one power supply. And the voltage drops, where are the voltage drops happening? At two places. One at the external resistor R, and another at the internal resistance small r of the power supply itself. So as you can see the equation below, it becomes, after applying KVL, total EMF E is equal to voltage drop across external resistor plus voltage drop across the internal resistor, and each of them is given as IR. Okay, R, capital R, is the external resistance, small r is the internal resistance, I is the current, E is the rated EMF, or the EMF, total EMF of the power supply. Now, the I capital R, the voltage drop or the potential difference available across the external resistor, it's something that we are usually interested in. For example, if I'm connecting a lamp or any component that I want to work, that I want to, see the working of in a circuit, I'm really interested in knowing how much potential difference will it be receiving across its terminals. So that voltage across the components terminals is given here as I into capital R. Let's call it the load voltage or the terminal voltage. What does it mean? It's the amount of voltage available for the external component. So we can call it the load voltage or the terminal voltage. Why terminal voltage? Because this is the voltage which appears across the terminals of the battery once the battery is connected in a circuit and there is a flow of current through it. Okay, so if I just replace I into capital R with the letter V, now this V represents the terminal potential difference or the load voltage or the terminal voltage of the circuit. Here on the slide, you can see we have just rearranged the equation. So we are trying to make V our subject because that is the value we are mostly interested in any circuit, that what is the terminal voltage or the load voltage we are receiving. So terminal voltage becomes equals to total EMF of the circuit, of the source, minus minus the voltage drop across the internal resistance of this source. So whatever is left behind, that is what we receive at the output. Okay. Now, what I'm going to do is in fact, just have a look again at this equation. Terminal voltage can be measured either across, for this simple circuit, it can be measured either across the resistor R, capital R, the external resistor R, by, connecting a voltmeter across it, or it can even be measured by connecting the a voltmeter across the terminals of the battery itself, because the battery will have an EMF being provided plus some small voltage drop through it. So the terminal voltage will appear across its two terminals. Now, if you consider the situation when there is no external resistor applied, or let's just say there is a switch which is open or off in a situation, in that case, there will be no flow of current through the circuit. And when there is no flow of a current through the circuit, you can look at the equation and it will make a lot of sense that the terminal potential difference or the terminal voltage or the load voltage becomes equals to the EMF, the rated EMF. So when no load is applied, terminal potential difference appears to be equal to the EMF, but when a current starts to flow through the circuit, this current or these flow of charges undergo a voltage drop within the power supply itself. Therefore, there will always be a potential drop within the power supply itself. Just to elaborate on the same point, we can see that we have plotted a graph here. By the way, in common everyday language, we can also call this voltage drop or across or within the EMF source as lost volts. Usually, we call it voltage drop within the source or within the power supply because of its internal resistance. Now, for the equation for a terminal potential difference, V equals E minus IR, if I try to plot terminal PD as a function of I, why are we doing this? Because just a while back we discussed that when there is no current through a circuit, the terminal PD is equal to the EMF, the rated EMF. But once a current starts to flow, this terminal PD value starts to decrease. So just to see this behavior, if we plot terminal voltage or load voltage as a function of the current I, we see a graph, kind of a graph that is shown over here. Initially, when current is zero, terminal PD is at its maximum value, which we can also call the y-intercept of this line over here. So at zero current, terminal PD will always be equal to the rated EMF. As the current increases, the terminal PD decreases. And if you look at the equation again, V equals E minus IR, and compare it to the standard equation of a straight line, Y equals mx plus c, E is the y-intercept, R turns out to be the gradient of this line. And since it is a line with a negative gradient, that's why in our equation also we see it as E minus IR. So if ever you are given a VI graph, a load voltage versus current graph, in such a situation for a circuit, for a similar circuit like shown over here on the screen, then to find the internal resistance of the supply, all you have to do is find the gradient of the line. And to find the EMF, the rated EMF, the maximum EMF, you just have to look at the y-intercept of the line. Okay, now this graph that we saw in the circuit that we just had a look at, this makes up our core practical number 8, the last core practical of AS. The investigation is to find the internal resistance of a source of EMF. I would want everybody to please go through page number 85 from the course book. This is a very simple investigation. We just need a circuit as simple as the one shown over here. But keep in mind, within the dotted box where they have shown the EMF source and a small internal resistance R, we do not use this as two separate components. This is just to represent, just a representation. Actually, our source of EMF itself, whatever it is, a battery or power supply, a cell, our source of EMF itself has both of these functions within itself, being a source of EMF as well as providing an internal resistance within it. So all we will need for this investigation will be a power supply, a source of EMF, and an external resistor R. And to find the internal resistance value of this particular source, we can have a graph something like the one shown on the screen, graph between terminal potential difference and the current. So which means we need to have some means of measuring the terminal potential difference and current in the circuit. So we can have one emitter connected in series with the external resistor, and we can have a voltmeter connected in parallel either with the across the load resistor or across the battery itself. So once we have those measurements, we can keep varying the current through the circuit, and for each value of the current we can note down the corresponding value of terminal PD to see how terminal potential difference changes as a function of the current I. And once we have the graph plotted, we can find the gradient of this graph. One more thing which we need to keep in mind, if you want to change the current in the circuit, we need to have not just a fixed resistor, instead a variable resistor, so we can vary its resistance and hence control the current in the circuit. Here's one exam style question related to internal resistance. I'll just go through each part of the question briefly, and then I'll show you the marking scheme at the end. Student investigated the EMF and internal resistance of a battery. The student connected a high resistance voltmeter across the battery. The battery was not connected to any other component. Explain why the reading on the voltmeter gave the EMF of the battery. So right now the load voltage or the terminal voltage comes out to be equal to the EMF. So why is it happening? Because if you think about it, in this till this part of the question, there is no external component connected to the battery, which means there is no complete circuit, there is no flow of current through the circuit, which means there is no voltage drop within the battery itself. So if you think about the equation for the terminal load voltage or terminal of the load voltage, V equals E minus IR, where IR is the internal resistance. Here, since current is zero, the terminal voltage should be equal to the EMF because there is no current through the circuit. So for 2 marks, you need to explain that since there is, because the questions, the command word over here is explained. So you will have to give the cause and the effect, some statement along with its reason. So since there is no external component connected to the circuit, there is no flow of current through the circuit, hence the terminal potential difference will be equal to the rated EMF because there is no voltage drop within the EMF, within the source of EMF itself. The student investigated how the potential difference across the battery varied with the current in the battery. Draw a circuit diagram for this investigation. This is the exactly same circuit diagram we were speaking about through our PPT. We will have an external resistor R, which we need to keep as a variable resistor. We need to have an emitter connected in series with it. We need to have a power supply and a voltmeter connected in parallel with the external resistor or the across the battery, either of the two. So that will be our circuit diagram. We'll have a look at it on the marking scheme as well. The student plotted her results on a graph as shown. This is a similar kind of graph that we were having a look at. Terminal potential difference versus the current. Determine the EMF and internal resistance of the battery. We have to, of course, use the graph for it because this question is exactly following the right after the graph. For 3 marks, you have to find EMF and internal resistance of the battery. Now, how will we do it from the graph? We know that the terminal potential difference is equal to the EMF when the current is zero. So you will look at the y-intercept of this graph that gives you a value for the EMF. And to find the internal resistance of the battery, what is our method? V equals E minus IR. Compare it to y equals mx plus c. So you will figure out that the gradient of the graph is equal to its internal resistance. So you will find the gradient of this graph, show it step by step, and you will definitely score the 3 marks over here. Write down the answers with the correct units. EMF is going to be in volts, internal resistance is going to be in ohms. Explain why there is a maximum current that can be supplied by the battery. Explain why there is a maximum current that can be supplied by the battery. So let's go back to the graph. Now in this graph, we can clearly see voltage or the terminal voltage keeps on dropping, becoming lesser as the current through the battery or current through the circuit increases, and the line stops at one point on the x-axis. So it reaches the x-axis beyond which it doesn't go. It stops right there. So the question is why there is this maximum value of current and the current cannot go further beyond this point. So for this thing, you can understand this from either through the graph or through the equation of terminal potential difference. So if you look at the graph, at this value of maximum value of current, the terminal potential difference becomes zero. Now, what does this mean? Now, think of the equation for the terminal or the load voltage. V equals E minus IR, where IR is the potential drop within the supply itself. As the current increases, the potential drop across within the EMF source itself increases. It will increase to a point till the potential drop within the battery itself becomes so high that it becomes equal to the EMF provided by it. So EMF minus the lost volts or the potential drop within the battery itself. When this term becomes zero, our terminal PD, the PD available across the load, becomes zero. Hence, we cannot have now any more current in the circuit. The circuit wouldn't work beyond this point if I try to increase the current further, because our system or our circuit cannot support any greater current, because higher current would mean that the internal resistance of our EMF source would need a further voltage drop, for which we do not have the means in the circuit. The EMF provided is much lesser. Okay, so this becomes our reason for this question. Now just have a quick look at this marking scheme. So you can see that the sample circuit that we were talking about is also shown over here. Calculations of EMF and the gradient of the graph to calculate internal resistance is also shown here. The last question, the 2 marks reasoning question, I can just quickly read it out to you. As the current in the battery increases, the potential difference across the internal resistance increases until the PD across the internal resistance equals the EMF. The current can no longer increase. Okay, so that's about it. You can find more past paper questions related to internal resistance. The idea still remains the same.